So we're finally at the point where we can start talking about the derivative of a function. And we start by introducing the notion of a derivative of a function at a given point A. In the next section, we'll start looking at the derivative as a function itself. But for now, we'll just discuss what happens when we look at the graph of a function f at the point A. Then what we do is we look at all these secant lines here and we compute the slopes. So if the slopes of the secant lines approach a limit that is the derivative of f at the point A. So this is the graph of the function f. And so as we get closer and closer to the point A and we record all the slopes of these secant lines, if those slopes are approaching a certain number, then we call that number the derivative of f at the point A. So we compute rates of change, average rates of change, and if those rates have a limit, then that will be the derivative. So in a formula, and of course this limit need not exist, but when it exists, it's called the derivative of f at the point A. So this is going to be the limit of f of x minus f of a divided by x minus a as x approaches a. So that's the formula that will define the derivative of f at the point at a given point. And this is something that came up actually in the last work session, one of the last quizzes. So you usually, in calculus, you often get expressions of the form, if you try to evaluate them, you get expressions that yield 0 over 0. And that's the whole point of studying calculus, how to deal with those kinds of expressions. They're not clearly defined. So, and the derivative is one such example. So if you try to plug in x equals a, you're going to get 0 on the top and the bottom. So the way to compute these limits is by looking at the previous sections and see what we've been doing. And so that means use algebraic manipulation or the squeeze theorem in order to obtain these limits. So in order not to avoiding evaluating at the point, because then we'll get something that's undefined. Okay, so that's the problem with the derivative. So if we try to just evaluate here, then we will get nonsense. Okay, so this is not equal to 0 over 0, and 0 over 0 is not 1, is not 0, is not anything. And we'll see with some examples how to actually compute the derivative at a point. So let's look at the following example. Find the derivative of f of x equals 1 over x at x equals 5. By definition, so we have to proceed by definition. And so what is f prime at the point 5 is the limit when x approaches 5 of f of x minus f5, all that divided by x minus 5. What is f of x according to this rule? We have to plug in 1 over x. Right, it's 1 over x. What is f of 5? Again, we appeal to the same rule. It tells us that we need to compute 1 over what's inside of f, so 1 over 5, and then that over x minus 5. Can we simply evaluate here and when x is equal to 5? No, we'll get 1 over 5 minus 1 over 5, which is 0, and we get 0 in the bottom as well. So we would get an expression 0, 0, which is not defined. Okay, so this is something we cannot do. So we need to continue manipulating this expression algebraically. So we put these two fractions together in the top. So that gives us 5 minus x divided by 5x. That's just the top. And then the bottom is x minus 5. We continue, this is equal to the limit of as x approaches 5 of I'm gonna write, well, we can write 5 minus x as minus x minus 5. When we distribute the minus inside, we'll get we'll switch the signs of x and 5 and minus 5, and then we divide this by x minus 5. And if we remember how to deal with fractions, this can be written as minus x minus 5 divided by now 5x times x minus 5, and then we can cancel the x minus 5s now, which gives us minus the limit of as x approaches 5 of minus 1 over 5x. Now this expression is well defined and it's continuous at the point 5, and so we simply evaluate at the point, right? This function here is continuous, and so we can plug in 5, so minus 1 over 5 times 5, so 5 squared, so it's minus 1 over 25. So just in case you are struggling with some of the more elementary algebraic steps in this derivation, what I did here is 1 over x minus 1 over 5 is the same, and we cross multiply, so it means that we multiply and divide by 5, so 5 over 5x minus 1 to get a common factor. We do x over 5x, and then they both have the same denominator, so we can put them together to obtain 5 minus x divided by 5x. So that's what transformed this into that. Okay, now for this other step here, whenever we have a fraction over a fraction, say a over b over c over d, this is the same as a over b times, and then we flip the fraction on the bottom, so we have d over c, which is then a times d over b times c. And this in particular tells us that when d is 1, which is the case here, so you're dividing x minus 5 by 1. So if you have a over b divided by c, because c is the same as c divided by 1, so then that will tell us that this is transformed into a times d, which is 1 over b times c. Okay, so this is exactly what we did here. And finally, if you struggle with this point, I wrote also that 5 minus x was equal to minus x minus 5. And this is true because if you bring the minus sign in here, distribute, you get minus times x. Minus minus becomes a plus, so it's 5 minus x. So this is actually true. Okay, so this is a kind of problem that appears often. So we will ask you to find the derivative of a function by using the definition. And it can be a polynomial. It can also be a power function like this. This is 1 over x. 1 over x is x to the minus 1. It could be 1 over x squared. And so things like that. So now that we computed this, let's use a more useful way of writing this derivative. So this is what we usually go for. So I already gave the definition of the derivative, but in practice we will always be computing that limit as the limit when h goes to 0 of f of a plus h minus f of a divided by h. So this is perhaps a more useful way of writing the derivative, definition of the derivative. And this is the definition. So this definition of the derivative. And so it's actually the same if you think about it. So if x is approaching a, then that means that x has to be a plus or minus something really small. So some h that is really small, so really close to 0. And what is x minus a? If x is equal to a plus h, then that's equal to a plus h minus a, and that gives you just h, which is exactly what we have here in the bottom. And that's exactly the same form we have up here, the original definition of the derivative. But you always compute these derivatives by definition by just writing, trusting the formula and writing what f of a plus h is and f of a, and then trying to compute the limit by doing some algebraic operations or using the squeeze theorem. More often than not, for the exam, you will only be asked to compute the derivatives by definition in cases of power functions or polynomials. Okay, so now let's go over on another definition that we need. So this is the tangent line. The whole purpose, geometrically at the beginning, was to obtain a notion of a tangent line. So by looking at the secant lines, we will obtain something that would be sort of tangent to the graph of f at a given point. So the tangent line passing at a point A, so the equation of the tangent line to the graph y equals f of x at the point P equals a comma f of a. It can be given in two forms, but in point slope in point slope form is y minus f of a equals f prime of a times x minus a. So this is just a formula. Geometrically, I mean, it's not hard to convince yourselves that this actually corresponds to the equation, the only candidate for the equation of the tangent line and the point. So what do we need here in order to compute the tangent line? We need the point A, the value of f, and the value of the derivative. So three things. So to compute so three things. To find the equation of the tangent line. A, f of a, and f prime of a. So now, so what do we mean by that? So let's look at an example. What happens if we're asked to find the equation of the tangent line to f of x equals x squared at x equals 3. So as we said, we need three things. So what is the point? The point A here is 3. F of A is, well, given by what f is. In this case, it's just raising what's inside f to the square. And in this case, it's just 3 squared. Remember that a is equal to 3. And we're missing now what is the value of f prime of a. F prime of 3. So we need to compute that. So what is f prime of 3 according to the definition is the limit when h approaches 0 of f of 3 plus h minus f at the point 3 divided by h. This is just a formula applied to this particular f and for this particular point A. If you go back to the definition, it's f of a plus h minus f of a divided by h, and you take the limit when h goes to 0. So it's just that in this case, we're computing the derivative at the point 3. Okay, so then if we do that, we compute the limit as h approaches 0 of what is f is 3 plus h is whatever you have inside squared. So 3 plus h squared minus 3 squared, all that divided by h. And this is the same as the limit when h approaches 0 of 3 squared plus h squared plus 2 times 3 times h minus 3 squared, all that divided by h. We just simply expanded 3 plus h squared. In case you forgot, x plus y squared is x squared plus y squared plus 2xy. And then we can cancel this out, and we have a common factor of h squared plus 6h, all of that divided by h, which is just the limit when h approaches 0 of, take out a factor of h plus 6 divided by h. We can cancel out the h now, and now this expression is no longer undefined when we plug in 0. So we can just plug in 0 here, and we get 6. So this is the value of the derivative of f at the point 3. And so now we have everything we need for the formula. So if we go back to the point slope form of the equation of the tangent line, we just say, so the equation of the tangent line, is then y minus f of a. What is f of a? We computed here, so f of a was 3 squared, so 9. 1 minus 9, and that's equal to f prime of at 3, which is 6. That's what we just computed, and x minus times x minus 3, because the point is a equals 3. And that is our equation for the tangent line. You can expand this and obtain a different expression for the different form of the equation for the tangent line, but this is enough. Okay. We'll continue with this on Thursday.